Wow, amazing. I cannot say too much that we are so lucky to live in the 21st century. 30 years ago, we talked about Internet of Things. Then after a few years, we talk about Internet of all things. Today, we're talking about not the internet. We talk about physical interactions of human beings and robots. So MIT, the top university on the earth that human beings created. I don't know whether in the future AI robot will create a university. So MIT has a challenge. But Taiwan, the most productive country to producing 1/3 of semiconductor on the earth. I'm just back from WSC, World Semiconductor Council. So one projection may be useful for you to know what semiconductor is doing today. 2 years ago, the semiconductor revenues, whole world, annual revenues are $800 billion. And DRAM, $90 billion. So this year, WSC agree, DRAM will become $560 billion. That's about 6 times. If you put the flash memory together, it's $800 billion. Then, what are the semiconductor revenue this year? I said $1.4 trillion. But the representative, the president of US SIA, Semiconductor Industry Association, said $1.5 trillion, Nikkei. So, I think it's very, very pleased for Taiwan audience here to receive EPOC and MIT distinguished professors traveling 1,000 miles and to have this symposium. And Professor Baha is one of the most respected person in our semiconductor industry. He make a lot of contributions. He has industry experience with TI, and now a professor with MIT. And the young professor I met last night, your talk is wonderful. I very enjoyed it. So today the topic, of course, is role-playing in physical AI, Taiwan Semiconductor, MIT invention. So I will ask each panelist one question, then I'll invite you to ask 2 questions, then I get another run to ask them each question, then we see how the time, okay? We may accept more questions. So I think since Professor Baha is here, he worked with Bell Lab on CMOS time, okay? So you must have a lot of things to express to us. How do you feeling that the semiconductor industry experienced explosive growth after scaling of Moore's law? Do you see a similar CMOS moment, CMOS experience coming for your now interested topic, molecular diagnostics and nanopore sensing? Sensing is so important. Physical AI really count on sensing. What key breakthroughs are still missing in your field? Please.
Thank you, Dr. Liu. As you said, it's an exciting time. We see the amazing exponential growth of the technology and innovation across the board. And what we see today is the pace of innovation is picking up. And amazingly, semiconductor is at the core of this innovation. The fact that we have these massive capabilities in AI, robotics that you're talking about, and every aspects of the physical AI and virtual AI is fueled by power of semiconductor. And this demand for higher performance and higher number of semiconductor, I think, is insatiable. It's not going to slow down. Just look around you and your pockets, how many gadgets you're carrying every day. It's just growing, from the ring that you're wearing to the watch to all the gadgets that you're carrying, and what you have around you, from robots to autonomous vehicles and everything. Just you need more and more intelligence, more and more connectivity, and they're all fueled by semiconductor. From my journey in Bell Labs all the way to the point that now we are talking about $1.5 trillion market, I don't think anything else in human history, any other technology, had the same pace of the growth and innovation. How many technologies you're aware of to get million times better and cheaper? I mean, can you imagine if your car was 1,000,000 times faster and lower cost, what you could have accomplished today? So I think when we see a CMOS success, another factor is that it took us many decades to get to the point that we have such a wonderful throughput and yield on manufacturing it, because one thing to prove the device, the other thing is that you ship billions and hundreds of billions of these devices for different applications. So I see the trajectory of the semiconductor is going to accelerate, but we need to have CMOS plus, meaning that not replacing CMOS necessarily, but adding more capabilities with new materials, even beyond silicon, not replacing silicon, but addition to silicon. And we have seen signs of that. I mean, this vertical structure for transistors and vertical structure for packaging, that's one example of that. Another example of that is when you combine different functionalities for sensing, for example, and for switching and for computing on the same device, you need to combine multiple technologies and add more capabilities. A great example of is medical. The reason that I'm very excited about the potential growth in semiconductor content of the medicine and medical application is that so far, most of the semiconductor in medicine has been in big machines, MRIs and CT scans and X-rays and so on. But we see the trend is changing. Not only we need more advanced machines and imaging technologies, but also we need to monitor dynamics of what's happening in your body. So you need to expose molecules to semiconductor. I was talking to the head of largest behavioral center and mental health institute in Boston, McLean Center, and the head of the science there said that if you can monitor hormones and biomarkers on a regular basis, we think we can predict or treat the onset of psychosis a lot better than what we are doing today. So that's a great example of how semiconductor can bring in new waves of personalized healthcare and higher precision healthcare. But it needs to be combined with physical domain, meaning that what I call it hybrid AI. You need to have an understanding of the structure of the body through these advanced machineries, imaging and lab tests. And then by monitoring the dynamics over time, you can add more value, because at the end of the day, a lot of these puzzles about our humans cannot be so episodic. You can, I mean, unless people are sick and need to be in the hospital environment. You need to monitor. I mean, a great example of that is I'm really excited to be part of this glucose monitoring journey, because people now can really look at different aspects of their life beyond just measuring the sugar in their blood. I mean, great example of that, there is a theory, and I'm not a biologist, so that's what I read in some of the latest publications. Insulin resistance is the source of many disease, including cancer in many cases, for many biological reasons. And guess what? We can look at the level of insulin resistance, but these patches. So you can see how much electronics and semiconductor can change the world. So the world I see ahead of us is more performance and more heterogeneity of the materials that we use in the semiconductor industry.
Thank you. And hybrid AI and let me think about one day the physical AI and the physical human beings will be integrated. Not digital twins, not lively twins. Anyway, I think this year, 2026, semiconductor has major structural change. Like Professor Bahar said, in the last 40 years, semiconductor always count down the increase of the volume and decrease the ASP, average selling price. But 2026, there are two trends. One thing is still the volume growth, but on the other hand, if the chip are valuable, their ASP growing fast. If the chip are for common consumer usage, it still continue to decrease. Average is increase. I've never seen that before, okay? And the second panelist is also outstanding. I knew him because he and my son, Tim Lu, are about the same age. But now he become MIT very distinguished associate professor, but of course, a professor in the future, and create a lot of new things. We are very glad that you visit Taiwan, and with your intelligence, we can learn how to handle the future physical AI. May I ask you a question? We are familiar with data scaling today, but you talk about physical understanding. So large language models scale with data, but the physical world obeys physics. In your view, will future robots succeed primarily from bigger and bigger model and more data, or through deeper understanding of force, motion, interaction with the real world, or both? Can you analyze for us? Yep.
Thank you for having me and for organizing this forum. I think going back to the question that you are asking, I do think data is an important part of making robotic systems become more general, because that's the one thing that we know from machine learning is as we get more diverse and good data, that leads to generalization. And that's the only recipe we know, how to get generalization. But having said that, the data that we have today is data in form of language and vision, which has been very good for training language models, vision models. But this data is not sufficient for us to figure out how to move the robot's fingers. Or think about if you're charging your mobile phone every day, you're inserting a cable, you're feeling the force. Or if you're picking up a raspberry versus a screw, the amount of force you're applying is different. So even if you looked at all of YouTube, yes, you have a lot of human motion, but you don't have this information about forces. So I do believe that force reasoning is important when the robot or a human has to perform actual manipulation. But there's also a level of building a plan, which might say if I want to cook dinner, what vegetables I have in my fridge, how do I bring them to my kitchen counter, then I have to chop them, put them in the pan. So I think doing this planning part is where vision and language is very important. It helps you understand the scene, it helps you understand what objects are there, and what steps need to be done. But how to execute these steps is where physical interactions and forces become important. So I think the answer is both. There is a role where language and vision has to do planning, and there's a role where force interactions has, which is to do control. And we need to scale up our data for these forceful interactions. The other thing I think is there is a lot of excitement about physical AI, but I don't think it's going to pan out in the same way as ChatGPT panned out, right? Where one day OpenAI released a model and everyone could start using ChatGPT and get excited about it. I think robotics is going to be more phase-wise. where we're going to see it getting applied to few applications first and slowly growing to more and more applications. So while we should be very excited, we should also be realist in how the technology is going to get adopted.
Thank you. So you can prepare your question. During this time, I tell you that for two professors, in Song Dynasty, about 1,000 years ago, the scholars in China are studying the 哲学, physical and philosophy, how to integrate together. Okay? So, of course, end up a lot of interesting things. For example, 民胞物语. Humans are my brothers, but we have to give everything benefits to people after we study the physics and physical human learning and living. So anyway, any question? Yes.
Again, thank you for the outstanding speech. I had a question for Professor Agro. You talk about the force interaction, but human hands has so many sensors in terms of touches. When you get feedbacks through force interaction, do you need these sensors for the robotic hand as well to distinguish such delicate feedbacks?
Yeah, so I think this is an open question that people are researching on in how much tactile sensing is needed. And at least from what we have found until now, is the more richer tactile sensing you have, the faster and more reliable your manipulation becomes. So if you only had vision, you can still perform the task, which is like if in winters, if you wear gloves, that makes your touch become much lesser. Humans can still do manipulation. It becomes much slower. And as you can feel more, you can go faster, you can be more reliable. So I think there are applications where force sensing may be less important, especially if you don't care about going that fast. And there are applications where force sensing will be more important, where you care about going fast, or it is more delicate manipulation that you have to do. Now, do we have to replicate everything a human has in terms of touch? I don't think so. But I think what is a spec for an ideal force sensor for robotic manipulation is still open.
Okay, let me continue the question to two distinguished professors. So Professor Baha, since you know semiconductor so well, I have to grab this opportunity to ask you. For Taiwan, we are so good in semiconductor manufacturing, but we are really now seek future opportunity. So where do you see the big opportunity, or at least some opportunity for Taiwan to participate in semiconductor-enabled AI chip, healthcare, and biosensing now you are interested in? What are our opportunity?
I think as you pointed out, semiconductor industry has made a tremendous impact on every aspect of our life and is growing very fast. But we are getting to the limits of what we can do with the traditional materials. And even though we have some runway left to scale up and making sure that we can get more performance, more density, higher switching, but if you look at some of the latest advanced chips, we are kind of like getting to the point of thermal limits rather than the number of transistors only. A lot of these companies that are working on AI infrastructure are hiring experts in thermodynamics, just how to manage the heat. So obviously, to get to the next level with all the tremendous amount of data, physical AI and all the other aspects of the virtual AI and data that we are using, we need to come up with more advanced materials, what we call it CMOS X. I mean, CMOS plus X really is that a new level of materials that can enhance the performance. And also, when it comes to things like biosensing, typically exposure of the semiconductor to molecules and liquid is not something we do. Usually we keep things hermetically sealed, we want to keep them as dry as possible after manufacturing. But in this case, now you are exposing it to fluids and the molecules that can impact the performance of semiconductor quite a bit. For example, the drift or biofouling or other phenomena, which is very unusual because for semiconductor guys, when we ship a satellite, we don't recall it after a few years to calibrate it. So it's up there. Or when you build a car, you expect to have 20, 25 years of reliability of the electronics in the car in most cases. So it brings a different paradigm of how to manufacture devices and how to test them and how to make sure that the performance is at the level that you can rely on it. Of course, in some applications, you need a short lifetime, like for example, a patch, you can replace it. But in general, you need to have the same type of reliability we have now in CMOS gates. Now you have hundreds of billions of transistors on a chip, and you're pretty sure every one of them works fine, and it doesn't kind of randomly change. When you expose it to chemicals, you need to look at it in a different way and learn how to manufacture it. So I think on the new materials and new applications, there is a lot of opportunities, and some of these are beyond and above what we are doing in a typical fab that is doing the traditional CMOS technology.
I see. Thank you. The next question to Professor Agrawal. Many people now question whether robotics when will have its own ChatGPT or brand moment. Are we approaching that inflection point? And what are still the major barriers prevent robots from achieving human level physical intelligence?
That's a very timely question. I think the tailwinds are there where we are advancing, hardware, we are advancing data, and that goes back to, what is one of the biggest challenges. I would say one of the biggest challenges is replicating human-like hand dexterity, and that involves, hardware. It also involves software, and the main challenge with software is we simply don't have data. Of the kind that I just, we were talking about earlier. And then, going back to, Professor, Ahmed's point about building things which are reliable. So when you go down to robotic systems, now you end up having moving parts. The more motors you put, the more chances there are of the system breaking down. So if you do want these systems to be reliable over a long period of time, I think there are many lab technologies where we have very good robotic hands, but transitioning them into a way that they can be deployed and be used, and the fact that robots have to be safe around humans, I think all of those are factors that we have to consider. So the question is, will there be a lab demo where you may see a robot doing many different things in an apartment? I think we're approaching that. But will there be an actual robot system deployed that you are going to buy in the next few years? I don't think we're anywhere close to that. Right, just to give some context, right, in 1989, we had self-driving cars which were demoed on highways. But then for that technology, even today, right, like yes, in 2026, we have Waymo, which has improved a lot, but still it's not free-form driving. So I think it's easy to think about technology as a demonstration and technology as something which we are starting to use into our daily lives. And this is why where I think that the ChatGPT moment is not going to be like one day you wake up and the moment has happened. What we'll see is gradually there is more adoption of robotic systems across a wider range of industries, where initially people thought about robotics only when they had applications which were high volume. But now we can start thinking about robotics where the application may not be high volume, or what people call mixed SKUs, or tasks where there are many different things, and each thing is low volume, and the robot can still start automating that. So I think that will happen much earlier. Then maybe we'll go into services, things like hospitals and hotels, where you need to do cleaning, you need to arrange the room. There's so many things, and then maybe eventually get into the house. So it's going to take a while, but I think it's very exciting because it seems it is possible, which is something which the feeling was not there, 3-4 years ago that it is possible. So I think that makes it super exciting to double down, both in terms of investment, but also, in terms of how much progress we can make. And maybe going back to your example, that you said there was progress in semiconductors, which was millionfold. So I think for me, when I think about it, like 5 years ago, you didn't think that was possible. And now you start thinking it's possible, and that is very exciting.
Thank you. Now, open the floor to the audience, waiting for one question. Before that, I'll do a test. If the traveling cost is below $500,000 US, are you willing, or you're quite happy to travel to the moon to live 1 week? And the guy like that, please raise your hand. Not too many. Okay, Taiwanese are too conservative. Okay, then easier question. Do you believe human beings versus physical AI with brains living the moon for 1 week, which come first? Which come earlier? You select human beings. Please raise your hand. Oh, good. And if physical AI robots, please raise your hand. Gee. Okay, I suggest Guangda or whatever, big guy. Okay, you say something.
I have a question for you.
Oh,
All of you.
okay.
In many civilizations, in many ancient civilizations,
Yes.
there are different phrases, but question is the same one. They said, money is the worst master, but the best slave. Now I want to turn question to AI. Okay, is AI a good slave or a good master?
Okay, he's a professional lawyer. I don't, quite surprised me, lawyers propose so scientific questions. Would you two, anyone want to answer his questions?
Yeah, maybe I can make a comment. I mean, I don't want to get too philosophical, so let me talk about more technology on that one. AI, almost in every field of technology and other disciplines, has proven to be a great co-pilot at this point. If you look at medicine or even manufacturing of the electronics or other fields, people who use AI efficiently have been much more productive. I can even translate how manufacturing with AI at semiconductor facilities can improve the performance, and how diagnostic in medicine can be impacted by AI. So as AI gets more and more mature, we see the impact as a co-pilot is getting more and more obvious and differentiating. Now, what's going to happen in the future, it's hard to tell. I mean, AI is not a new thing. I think the first AI lab was in 1950-something at MIT, but by McCarthy and Minsky, so it's about 7 years old, the technology, and it's getting better and better. So is it going to be in the future more than a co-pilot? It's conceivable, but then a lot of things come up, like ethics for robots and how things can get regulated. But obviously, what happened with Anthropic like last week or last few days was very telling. I mean, the new software that came out can break to any secret code that government has. So it can changes the entire way of protecting confidentials, doing business. So the impact is huge. But I think for foreseeable future, it would be more co-pilot than a pilot.
Okay. I saw the young generation of Taiwan. Are you below 40 years old? Anyone below 40 years old want to grab this opportunity? Okay, that gentleman, sorry for this, okay? Yes, please.
Hello. Thank you for the speech today. So, as we all know, currently, in order to achieve like affordable physical intelligence, we face like a massive bottleneck in scaling this intelligence for mass adoption. There's a lot of issues such as silicon wafer prices in, say, leading fabs such as TSMC that are facing demand that exceeds the capacity of the current infrastructure for production, which leads to the current GPU and memory shortages. So given that like true lifelong learning requires robots to constantly adapt in the real world with a lot of complex force touch data under thermal and maybe also power limit constraints, the current reliance on heavy cloud compute power, megawatts of electricity, and massive onboard GPU clusters for AI training and inference really creates a major barrier to mass adoption. So from your perspective, is there any solution to, say, power-constrained edge training to implement all these strategies in order to achieve the level of physical intelligence that are necessary in, say, neuromorphic hardware and maybe some specialized edge AI accelerators, or maybe some software-level optimizations like the current QAT, mixture of experts, and sparse on-device training going to be the primary drivers for lifelong learning? Thank you.
I was surprised the young man asked so long questions. I didn't catch the meaning. Any one of you? Maybe Professor, you are younger. I really don't catch what you want.
Yeah, I think it's a good question. I think a lot of the resources in terms of GPUs and chips are getting used by large language models today. And a lot more is now getting focused on actual serving users instead of it being only used for doing R&D. I think physical AI is still in the space where a lot of R&D is still required. So in the next maybe 2 years, I don't see that becoming a challenge, and maybe our friends who study chips can help solve that problem that chips are facing. But definitely there are also alternatives that people are exploring in terms of how do we design our chips, in terms of how do we manage memory and how memory and data can sit together, which can help machine learning becoming more efficient, being less power hungry. And I think there are also things we can definitely do in terms of software, where we can try to minimize the number of flops required to do computation, right? For example, if your model is hierarchical, for every action, you don't have to use the full big model. You might be able to use parts of the model for some actions. And for doing more advanced reasoning, you might call a bigger model. So I think it's a system-level optimization problem. So I would say definitely things to be done on software, and hopefully our friends are going to build better chips.
I add maybe a couple of comments in addition to what you mentioned. It's a very good question, actually. There are multiple trends happening. This is very interesting, especially for next 2 years. Part of it is a typical cyclic nature of semiconductor. You underinvest, and then market picks up, and it takes 5 years to make a new fab and $10 billion plus. So that's always a challenge. Sometimes it's oversupply and undersupply. So that's part of the last 50 years of going up and down. But something unique happening now that is kind of interesting, and that's why all of a sudden market is jumping to 1.5. I think there are 3 aspects of it. One is that because of the high excitement about AI, of course, the demand for everything, from power devices to GPUs to optical photonics, silicon photonics to advanced clocking, everything is going up. But it's not sustainable the way it is now. And there are 3 trends that really is going to hopefully change that and gives us more opportunity for growth. One is the fact that, as you know, LLM is not a very efficient approach for AI. It's large language models. I mean, as you saw earlier this year, this reasoning model managed to improve the algorithm significantly in terms of processing power capabilities. The second one is architectural aspects of AI. So if you have federated learning so that you go from cloud to the edge and then do the learning at the right point and training, that can also offload some of the heavy processing requirements. And third one is the new devices. Unfortunately, new devices takes time. I mean, it's not something that in 6 months you can have a new material or a new device. It took us multiple decades to get CMOS to where we are today. And memory, high bandwidth memories, and these high performance computing. So these 3 trends, new algorithms, which is the fastest rewarding, most rewarding breakthrough within the next few years, the architectural, and then in the long run, new devices, hopefully fuels more innovation in the entire field of material science, software, AI, and everything in between.
We have only 3 minutes left. I have a lot of questions, so I decided to let the gentleman to ask a question, and we give them short answers. I think we can talk about this panel for another 1 hour, but this is our last 3 minutes.
In the bar to like 45 now.
Maybe louder.
Oh, sure. I say like thank you to lower the bar to 45 now. I have a question for Agwo, Professor Agwo. First of all, what you're showing is very cool. It's almost feeling like watching a sci-fi movie, looking at those robotic arm. I have a question just out of my curiosity. Looking at one of the movie, you showed this Oreo rolling on the pressure, these pressure sensors. I noticed compared with real human hand, which you can feel maybe the human hair, even the dust, those maybe tens of micron sensitivity, and then with probably human hand with much higher density and also much sensitive pressure sensing.
Rich question as soon as possible.
So the question is how far do you think we are away from that human hand, real human hand comparable sensitivity, and then what's the potential limitation from the current technology to the human hand level sensitivity? Will it be the manufacture difficulty of the sensor density, or will it be the computation power? So what's the potential limitation, if there's any?
Yeah, so I think it's easy to get fascinated with the human hand in its full form. I think a good example is with flight, right? I mean, birds have feathers, but we were able to extract principles, and then we made a plane. So I don't think the goal of robotics is to mimic a human hand. Some aspects of human hands are there for doing manipulation, and some aspects are also very social, right? I mean, the sense of touch is fundamental to many relationships that humans establish. So I would say we can get, quite far, even without, getting to that resolution where you can feel the dust, or for example, you can feel vibrations, and there are many different kinds of sensing that one can feel. Now there are, so one way to think about it is what will get me to 90% of what we can do, and 90% of a $60 trillion economy is huge. So I think even before getting to human-like tactile sensors, with technology that we see today, but may not have been ready in terms of mass production, I think a lot can be done. And of course, with new materials, there is potential to expand that so that we can do that last 10%, which we may not be able to do with the current sensing which is available.
Okay, perfect time. Look at the clock, perfect time. So I want to show our special appreciation to both of you, and also, of course, the distinguished speaker today from MIT. And I think we learned a lot. We hope to keep more interaction with this Epoch platform, so both of us can grow together. Thank you so much. Thank you for everybody's attention. Let's get applause.